So, a couple things about this video. First, we're going to write some runjags code. It's going to prepare the data for us and construct a model statement. And then what we're going to see is how this model statement is going to enable runjags to implement Markov chain Monte Carlo algorithm. So we're going to begin with review of Markov chain Monte Carlo. So there's Bayes' theorem. The denominator is very difficult to determine, so we'll just get rid of it. Replace this with a proportionality sign. And then what we're going to do is we're going to take a large number of random samples of this thing, and that will give us the probability of this thing, because these two guys are proportional. So the way this is going to work is we're going to have a current value of theta, and then we're going to have a proposed value of theta. And we're going to get our proposed value of theta by taking the current value of theta and adding some small amount to it, where that some small amount is as a random draw from a normal distribution with mean 0 and standard deviation sigma. So then what we're going to do is for both theta current and theta proposed, we're going to evaluate both the likelihood function and the prior probability. So we're going to do that for proposed and the current values of theta, and we're going to calculate this ratio. And once we have this ratio, we're going to implement the following accept-reject rule that says the probability of accepting the proposed value of theta is given by this expression here, which means that if this ratio is greater than 1, then the lesser of these two values is going to be 1, and we'll accept theta proposed. That will then become the new theta current. On the other hand, if this ratio is less than 1, then the probability of accepting the proposed value of theta is going to be equal to that ratio. And so last week, we saw this MC by hand that implemented this Markov chain Monte Carlo for the handedness experiment. I wrote all this code, and there's the posterior distribution with the posterior that we got from conjugate superimposed. But I mean, this is really nasty code, and all I got from it was this kind of crappy looking posterior distribution. So what we're going to have is runjags, which first of all is going to enable us to use much simpler code, and secondly, we're going to get much better graphics. So if we're going to use runjags, one of the things we have to do is prepare the data. So we're going to be dealing with the handedness experiment, which is about as simple as an experiment as you can imagine. The data consists of 9 successes, 9 right-handed people out of n is equal to 10 that were sampled. And so we're going to take those data and we're going to make a list out of them using the asList function. And we're going to name that list data file. This next step doesn't have to be done, but it's probably worthwhile doing, is to look at the structure of data file, and you can see that, in fact, it is a list. It consists of these two items, the value of y, which is equal to 9, the value of n, which is equal to 10. And then we're going to take this object data file, we're going to operate on it with the dump format function, and that's going to create a new object called data for jags that runjags can interpret. And so now we're going to move to the heart of runjags, and that is the model statement. So there's the model statement, and we're going to create an object that I'm going to call my model. Any valid RNA would work. And the code consists of open quotation mark, the keyword model typed in just like that, open curly brace, and at the bottom we're going to close it off with a close curly brace and a close quotation mark. And in the middle, what we're going to have is, again, the essence of our model statement. And here is the DAG, directed acyclic graph, for the handedness experiment. And as was stated earlier, the idea is if we do our DAG correctly, then each one of these arrows will translate into one line of code in our model statement. So if we look at a directed acyclic graph, what do we see? Well, we start at the bottom as always and say that the number of successes arose as a random draw. Stochasticity is indicated by this tilde. The fact that it arises from a draw is indicated by this arrow. Number of successes arise as a random draw from a binomial distribution with parameter theta, which is our object of interest, and n, which in this case is equal to 10. So if we look at our model statement, we capture that here with saying that the value of y arises as a random draw from a binomial distribution with parameters theta, what we're interested in, and n, and we've told it that n is going to be equal to 10. And then if we look up here, well, we see that the prior distribution for theta was a beta 4-2 based upon having previously seen 4 right-handed and 2 left-handed people. And there we see it here, theta distributed beta distribution with parameters 4 and 2. These two items here, because we've got this pound sign, these are just comments that are not going to be executed. In this particular case, I put the prior first, followed by the likelihood. Doesn't have to be done that way. I could reverse the order and everything would be just fine. But in any event, we provided enough information that runjags can do the Markov chain Monte Carlo. Because remember, the whole idea is it needs to be able to evaluate both the likelihood and the prior for both proposed and current values of theta. And we've given it enough information that it can do that. So we're going to set this thing on a random walk. It's going to go through probably 10,000 iterations of this. At each step, it's going to evaluate the likelihood, and it's going to obtain the prior probability for both theta proposed and theta current. So in terms of the likelihood function, n is equal to 10, y is equal to 9, and you can put in either theta proposed or theta current here. In terms of the prior probability density, A is equal to 4, B is equal to 2. You can put in the value of theta current, theta proposed, and out will come the prior probability density. So we go through that 10,000 iterations. At each iteration, we keep a tally of theta current. And here you can see the different values of theta current through our 1,000 iterations. And there is the histogram that we get. If we take this histogram, divide by the number of iterations, that's going to give us our posterior distribution. So what I've just gone over is the code for data preparation, and the model statement hopefully get some idea of how runjags is able to implement this Markov chain Monte Carlo algorithm. And in the next video, we'll look at the results.